Ladies and gentlemen, welcome. This is Dr. Derek Ong, and I will be doing a quick um, run through of the kind of quantitative analysis that you need to select when you are doing certain analysis that you need. Okay, so let's start by looking at the process of quantitative analysis. Now, this is just a full process. It's not a must that you must do everything. It really depends on what is your objective. Usually, when we get a data back in, we will always want to do the descriptive statistics to look at the overall summary of the data. And then if we're doing something with multi-item analysis, then we will have to basically do the reliability testing for those items when we do our pilot tests. And after we do our pilot tests, we collect our data. We need to then explore the factor analysis to make sure that the data the items fit well into the particular factor. So let's assume that we are working with single items, and once we're done with single items, uh, we make sure that our variables are set. Then we can move on to do our t-test and ANOVA, looking at differences. And we can also then move on to using multiple linear regression to test for relationships. And of course, if we're using multi-item analysis, we can also think about using structural equation modeling. We can also test for moderation and mediation. And if we do not have any hypothesis, then if let's say we are interested in uh, traversing the data or just looking at the data mining, then we can look into heuristic data mining using cluster, discriminant, decision tree, or even perceptual maps. For this presentation, I will only be concentrating on stage 1, stage 5, which is t-test, the stage 6, which is the multiple linear regression, and of course stage 7. So bear with me with this one. So before we move on, let's talk a little bit about statistics. Now, statistics, there are actually what is it all about? It's basically a branch of mathematics that transforms data into useful information for decision making. And there are two branches. One is the descriptive statistics, where we describe about the statistics using summary and basically talking about the sample. And once we've done talking about the sample, then we want to see if we can infer what we found in the sample to the population, and that's where we have our inferential statistics. And we do this also using hypothesis testing to find out for differences and relationships. And we want to see if we could draw conclusions and make decisions concerning a population based only on the sample data. So descriptive statistics is fairly simple. There are two main measures that we explain about our data. One is called the measures of central tendency, where we use mode, medium, and mean to talk about the central point of our sample. And of course, we want to also look at measures of variability to see how dispersed our data is using the variance, standard deviation, or even range. Whereas inferential statistics would mean that we take from the population a certain sample, and then we estimate the population, let's say mean weight, using the sample mean. So we are basically estimating to see whether the sample mean is the same as the population mean, which means that we are inferring to the sample. And we do this, as I mentioned again, through hypothesis testings, drawing conclusions, or making decisions concerning a population based only on the sample results. There is this term that we often get mixed up between parametric and non-parametric. So basically, parametric testing is where we assume the data is in metric form, which is quantitative and normally distributed, and uses mostly the mean to calculate statistical measures. Whereas non-parametric data assumes that the data is non-metric and non-normally distributed, and this one usually uses the median to calculate the statistical measures. Now, for this presentation, we're only going to be concerning about the parametric testing, and we are not going to be concerning with the non-parametric for now. Now, sorry, this is not supposed to be conclusion. Anyway, this is just a quadrant that we are going to look at when we talk about relationships between data. So if you notice that we have quantitative at the side and categorical variables here, quantitative and also again categorical, which either it's nominal or ordinal data. We're going to be looking at these four quadrants where when we want to talk about the relationship between a quantitative scale measurement and a categorical variable, we would look into this quadrant here, and the other quadrants will then follow suit. So let's just start with this quadrant first. So differences. When we look at differences, we say that one sample t-test, we test the claims that a population mean is the same as a sample mean is the same as the population mean. So for example, say we want to test the claim that the population mean weight is 120 pounds. And if we have two independent populations, for example, male and female, then this will be what we know as independent. So we want to see if there's a difference between male and female in terms of, let's say, mean weight for males and females. So these two populations must be independent of each other. Then there is also the related samples, where we also want to test for before and after cases. The difference between the related and the two sample t-test is that the two sample t-tests, we have two samples that are independent, whereas for related samples, it really depends on the unit of analysis. So for example, if our unit of analysis is, for example, blood sugar levels before and after a drug administration, usually for each person we'll be taking your blood level before you administer the drug and then after you administer the drug. So that means we want to test to see if the drug was successful in lowering down your blood pressure. So that's the cases when we use related. So very important to understand the difference when to use two sample t-tests and when to use related sample t-tests. Two sample t-tests, there's always two independent population, whereas in related samples, there's only one population, but we take the data twice from each of the participants. Then, of course, there's the analysis of variance, where we are looking at more than two groups. This one here, we're looking at differences for two groups, but here we're looking at differences in more than two groups. So, for example, we want to test the claim or that the population mean weight is different between races, whereby races we know has more than two groups. And of course, if there is only one dependent variable, we use ANOVA, but if we have more than one dependent variable, then we need to look at multiple analysis of variance, weight and height, and of course between more than two groups. So here's an example. If we want to test for t-tests, gender, of course, is two levels, so we want to test the satisfaction level between gender, male and female. Also in experimental design, as I mentioned, we want to see whether there's a difference in sales before and sales after for probably a particular store or different ranges of stores. We just want to see if there was a difference between the sales. If we're looking at one-way ANOVA, I'm going to explain a little bit more about what this one-way means in a short time. So this education level has more than two levels, probably no schooling, high school, university degree, and then postgraduate, so that's more than 2 levels. And we want to see if there's a difference in satisfaction level. So there's a one-way ANOVA. And if we have control variables, now let me explain what control variables is. Control variables are basically variables that we are not interested to study, but it could have an effect on the results that we want to do. So, for instance, if we want to study purchase intention if there is a difference of purchase intention between levels of probably geographical areas that we stay in. One of the variables that we're not interested in studying but could have an effect on the study could be personal income. Yeah, because we know that personal income could confound or have an effect on how much we can spend. So we might want to set that in as a control variable to control for the effects of personal income to actually see if there is a difference in purchase intention. All right. So if we're going to add in a control variable, then we would have to add in the covariate. For if we're doing ANOVA, it would be called ANCOVA, and if we do a MANOVA, it would be called MANCOVA. And if, let's say, we want to do differences over time, let's say if it's more than 2 times, just like the repeated measures, that means we are repeating the measure for more than twice. So, for example, if we want to see the effect of a promotion on sales, so we could probably take data from three time frames: pre-sales, during the sales, and after the sales. So we just want to see if there's a difference over time on these sales, right? So for example, repeated measures: sales at time 1, sales at time 2, and sales at time 3. So this could be pre, this could be during, this could be post. So in the same branch, we want to see if there was a difference in sales with these time intervals. And that's repeated measures of ANOVA. Now, if we're doing a two-way ANOVA, means that we will be having 2 different sources of independent variables upon the continuous variable, which is the dependent variable. So here we want to see if there's a difference between gender, subordinate, and between supervisor gender on performance. Now, I know that some of you are getting a bit confused about when do we use ANOVA, when do we use MANOVA, when do we use one way, when do we use two way. So I hope that this particular table will give you a bit of an explanation. So for instance, if we're looking at just one dependent variable, for example, satisfaction, then we are only looking at ANOVA, which is analysis of variance. Also remember that we are talking about more than 2 categories here for the independent variables. So if we are looking at one independent variable with more than 2 categories, then we are actually looking at the difference in the dependent variable by the independent variable categories. If we're dealing with 2 independent variables, now it doesn't matter whether it's more than 2 categories or 3 categories, it really doesn't matter. But what matters is we're dealing with 2 independent variables here. Then this is what we mean by a two-way. And if it's one dependent variable, then it would be a two-way ANOVA. Now in a two-way ANOVA, we are basically looking at the difference in the dependent variable by the independent variable of one category. We're looking, variable 1 categories, difference in the dependent variable by independent variable 2 categories, and there is an added hypothesis that we need to check, whereby we will have to look for the interaction of the 2 independent variables. So for example, you might have race and gender. If we have 3 races, and 2 gender, then it will probably produce for us 6 categories. For example, Malay male, Indian male, and Chinese male, Malay female, female Indian, and female Chinese. So here we are looking at whether there's a difference across 2 categories, let's say gender, and here we're looking at 3 categories, let's say race. But here we're looking at difference between 6 categories, which is the interaction, you usually call it. So we are checking for 1, 2, 3 hypothesis when we do a two-way ANOVA. Now, extending this idea of the two-way ANOVA, if we have more than one dependent variable, let's say we want to look at age and height together as the dependent variable. If it's one independent variable, then it becomes one-way ANOVA. And of course, extending this, if it's two-way ANOVA, same thing again. Across all the dependent variables, we'll be looking at the differences. If you notice the variables here, and this has no S, so it's the same. It's just that we just add on one more level of um, analysis. So again, same here. Differences in dependent variables by the interaction of the 2 independent variables. Now, a word of caution. Usually we do not go more than two-way, because when it becomes three-way, it gets a little bit difficult. So please do bear in mind with that one. Okay, so we are done with this quadrant. Now we're going to look into the next quadrant. In fact, we've done these 2 quadrants actually. Yeah, we've done these 2 quadrants, because this quadrant looks at 1 sample and 2 sample, whereas this one looks at if your categorical has more than 3 categories or more, two categories or more. Now I'm going to look at this quadrant here. Let me just change my pen purple. This is where we are looking at categorical variables and categorical variables using chi-square test of association. So we're looking at relationships, and for example, we want to look at a categorical variable called gender and wearing spectacles. So if you know gender, you have male, female, and wearing spectacles, you probably just have yes or no. For example, level of study and owning a pet. So it is categorical, level of study, owning a pet. You do not count it. You do not have 0 points. So it's basically categorical variables. So it involves frequency tabulation and ends up with a m times n matrix, which is m, the number of categories in variable 1, and n number of categories in variable 2. So we use the chi-square test of independence to calculate, to show the existence of relationship. Now, I'm going to see if I can draw the chi-square out. Okay, that doesn't look right. But anyway, that is what we're going to look at, the chi-square, to check whether or not there is a test of association. So usually our hypothesis would be there is a relationship, the two variables are dependent of each other, and so on and so forth. So for example, gender and decision to buy. Usually decision to buy would be either yes, no, or probably you can add on undecided and nominal. So using the frequency tabulation and all, we will be able to test if there is an independence. So for example, let's say whether there's a relationship between attitudes of management decision and gender. So these are what we know as the frequency observed, and we calculate this against the frequency expected, and we check our chi-square against the chi-square table. So this is categorical and categorical. Finally, if we're looking at quantitative and quantitative measures, then we would have to look into correlation and regression. So this relationships is between 2 quantitative variables, whereby we use correlation coefficient to measure the strength and the linear relationship, which means we assume that it's a straight line relationship between two quantitative variables. There is a formula here, which this is how we calculate the coefficient of correlation, but I'm not going to go into that because I don't want to scare you. So let's just move on. Now, once we calculate correlation, our correlation between two quantitative variables can range from -1 to +1, whereby if your Pearson's R, which is the correlation, is a negative, then you get the relationship like this. If it's more than 1, then you get the relationship which is a positive relationship. And if it centers around 0, then probably you won't see any relationship at all. So between two quantitative variables, whether it's interval or ratio, satisfaction commitment, we use the correlation. But do note that correlation doesn't mean causation. Yeah, I've always used this example in the class. You and your sibling, that is correlation, but you and your parents, that is causation. So causation usually has a independent and a dependent variable. So causation is described using regression. When one variable causes the variability of another variable. So usually this one variable here is the independent variable, and this is usually the dependent variable. For example, advertising budget causes sales, or you can also say that sales depends on how much we spend on advertising budget. Supply causes demand, or it could be the other way around. Smoking causes cancer, and you can think of more examples on your own. Now, usually when we want to hypothesize causation, we hypothesize using theory. So theory needs to guide us when we hypothesize causation. So please remember that. So this is a sample of what we mean by theory. We know that service quality and product quality, higher the quality, higher we get in terms of our satisfaction. So this is a example of called regression causation. So if we have more than one variable in terms of our independent variables, yeah, then this is what we call, and this is the dependent variable, intention to share. This is what we call as the multivariate or multiple linear regression, yeah. But make sure that all the variables are of metric. Yeah, we can only do multiple linear regression as on metric. Just remember which quadrant we're looking at. And we can also have a mediation regression whereby we have something that sits right in the middle between the independent and the dependent variables. So, for example, here we say that attitude mediates subjective norms and perceived behavior control with intention to share. We can also have moderating variables. Now, moderating variables usually, the moderating variable can be a continuous variable, or it also can be a categorical variable. So we can also use, for example, gender here, and we say that if there is a moderating variable, we say that social class and frequency of dining out is moderated by gender. So if I were to draw something right here, yeah, let's say this F here represents frequency of dining out and social class. Now, if there is a relationship between social class and frequency of dining out, so for example, if we say that the higher you are in frequency, social class, the more you go out to eat, so our relationship would look something like this. But if we say that gender moderates this relationship, then what we might see would be something like this. Let me just change. Okay. So now the red line here represents perhaps male, and the blue line here represents the female. So if we say that gender moderates this relationship, social class to frequency of dining out, then we will get a graph like this, and with varying degrees of slopes. So here is a classic case whereby uh, the relationship of social class and frequency of dining out affects the females more than it does the males. So it means that females, um, the faster they move in the social class, the more they will frequently dine out. Whereas for the males, the social class doesn't really affect the frequency of dining out, but it does in a way, right? And we can also do this for quantitative variables like age. So age, if let's say we could have a high age here and a low age here. So we could say that for those who are of a who age or higher age or older, the social class and the frequency of dining out has a stronger relationship, whereas for the younger, it doesn't really matter much, yeah, or that all. So, having said all that, could you see if you know how to answer these questions, whether these are descriptive, inference, correlation, or causation? So, number of males in a sample, it's just basically describing a sample, so it's probably descriptive. Population income mean, and this is definitely inference because we are inferring the sample to the population. Speed of doing math and intelligence. Now, these two are um, quantitative variables, so neither are we postulating a causation, so this one is definitely, um, you know, sorry, this is a causation because we say that if you're more intelligent, then you can do maths faster. Rain and presence of umbrella, sorry, if there is rain, then probably there'll be an umbrella. And number of wins on the lottery and frequency of numbers. Now, these two could be correlated, but they are not causing each other. How about identifying the types of analysis for this one? Determining the factors that influence social misconduct among young females in secondary schools. So firstly, find out that social misconduct and young females. So are we saying that where are our variables? Actually, our variables are here, factors and social misconduct. So this is definitely a regression analysis. Yeah, because independent variables and dependent variable. The young females in secondary school is just for me to throw you guys off. Okay, so the next one is, oops, I missed out a bullet point. Understanding demographic breakdown of a mall shoppers in Sunway Pyramid. So this is definitely a descriptive. So we're just describing about the sample. Is there a relationship between one's sexual orientation? Now, sexual orientation is categorical, and highest education achieved. This is also categorical. So, categorical and categorical, that would be categorical chi-square analysis. And deciding whether a drug has been successful in reducing viral load in patient. Um, this would be definitely we want to check for viral load before and after. So if it's a before and after, it's definitely paired sample t-tests or related sample t-tests to check whether the drug has been successful. Last one. Do higher income earners have stronger familial attitudes that lead to better social concern of elderly? This, we actually have a few um, variables here. We have familial attitudes, sorry, we have social concern and familial attitudes here, and we have income earners, high income earners, and then the low income earners, right? So basically what we're trying to say is, does um, earning higher income have a stronger familial attitude toward and lead to better social concern? So this is definitely a moderating variable, right? Anxiety affects rumination and causes depressive state. What do you think this is? There are three states. Yes, you're right. This is definitely mediating variable or mediation. Investigating the difference between older and younger males in terms of gym going habits. So gym going habits here is quantitative. Older and younger males are just basically two independent sample t-tests. So we're looking at the two independent samples. Does traveling costs for work vary between levels of employment? Now, we assume that levels of employment here is more than two categories, and this is a categorical variable. This traveling costs is, of course, a quantitative variable, and hence we are looking at ANOVA. Organizational commitment and performance seem different between gender and race. This is interesting. Two dependent variables, organizational commitment and performance, and two independent variables. Yes, it's a maneuver. To be more precise, it's a two-way maneuver. Now, if you have any problems trying to understand this, please do email me or send me a message. But I hope you've enjoyed and learned something when selecting the right analysis. Thank you.